So, now another definition. So, omega f is called a measurable space. Again another terminology. Okay. So, at the beginning we will introduce a bunch of terminologies. So, what is a measurable space? It is some set omega endowed with a sigma algebra of subsets, right. The pair omega comma f is called a measurable space. Okay. This f can be any sigma algebra, it does not have to be any of these particular ones, or it does not have to be any particular sigma algebra on omega. As long as you endow omega with some sigma algebra f, this omega f is called a measurable space. Okay. So, the one thing that you should know about probability theory is that it is actually just a special case of measure theory, okay. And probabilities are simply special cases of measures, okay, which is why some people talk of probability measure. Now, have you heard that? Have you heard that terminology? You do not just say probability, but say probability measure, right. So, it is a special case of a mathematical concept called a measure, which we will define very soon. Okay. Okay, so let us define a measure. This is definition. Okay. So, measure is a function mu from f to 0 infinity included such that mu of phi is always 0, and number 2, if a1 a2 dot 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 is collection of disjoint f measurable sets, then the measure of the union, countable union of a I is equal to okay. So, that is the definition of a measure. Okay. Yeah. So, it is a mapping from so you are given some measurable space omega comma f, right, and so this measure is a function from f to 0 infinity included. Okay. So, it can actually take values. So, it can take any real value or it can take the value plus infinity. So, it is not just a real valued function, it is an extended real valued function. So, it takes values from 0 infinity included. Okay. And so, what does this mean? You are assigning measures to what? Subsets, not all subsets of omega. I want to make this very clear, only f measurable subsets. Okay. So, measures are assigned not to all subsets of omega, but to those subsets which you have decided to include in your sigma algebra, right, which is a judgment call you already made, let us say, depending on what you think is interesting to you. You have created some sigma algebra f and you say omega f is my measurable space. Why is it called a measurable space? I am going to put measures on this space. It is something you can put. What is a measurable space? After all, it is something you can put a measure on, right. That is why it is called a measurable space. It is a very this is actually a fairly simple definition. So, it takes as input f measurable sets and produces a real number or plus infinity, positive real number or plus infinity, right, and does not take negative values, that is all. It takes all values from 0 to plus infinity. We must necessarily have that the measure of the null set is 0. Okay. Now, so this null set, remember this null set is in F, so which is why we impose this condition, no, remember this. So, the null set is always f measurable, right, and that specific f measurable set phi has measure 0 always, okay. It is one of the axioms of measure. Okay. The second axiom of measure is known as the countable additivity axiom. Okay. So, this says that if I have a bunch of a countable collection of disjoint f measurable sets, then the measure of the countable union is equal to the sum of the individual measures. Okay. See, these ai's are after all f measurable. So, mu of ai is well defined, right, is some positive number, right. And also since ai's are f measurable, the countable union is f measurable, right. So, mu is also defined for the countable union, right. So, and the axiom imposes that if you take disjoint ai's, so if I have some big sample space omega and I have disjoint events, disjoint f measurable sets, right. Disjoint means they do not have, each of these ai's have null intersection, correct. So, ai intersection aj is null for all ij, that is what disjoint means, right. So, if I take the measure of the union of ai's, right. So, I am only drawing a finite number of them obviously, but there are actually a countably infinite number of these ai's, they are all disjoint pairwise, right. And if I take the measure of all these guys, the union of all that guys is equal to the addition of the measures of each of them. It is actually very intuitive, come to think of it. Think of measure as something that says how much is contained in there or something like that, right. So, if they are disjoint, I want to be able to add the measures, right. So, there are these two axioms. Okay. Yes.
This measure is nothing but probability measure, right?
No, I am talking about a generic measure. Okay. A measure is a function from your, so it is a function that maps f measurable sets to 0 infinity and you impose two conditions, right. One is that the null set should have 0 measure, the other is that if I have disjoint countable, so the countable union of disjoint f measurable sets, the measures can be added up, right. This axiom, if you note down, is called the countable additivity axiom. Okay. This is actually the function, this is the most important one, right. This is a fairly trivial one, this is the most important property of a measure. Now, the triple you just let us say the triple omega f mu, right. So, now you have defined some measure on this measurable space. So, you started with omega and then you endowed it with a sigma algebra f. So, this pair you called a measurable space in anticipation that you are going to put a measure on this space. Now that you put a measure on this space, this is called a measure space. Okay. Now it has a measure. Okay. okay, a measure space. So, what is a measure space? It is a triple consisting of a set, a sigma algebra on that of subsets, and then a measure defined on the F measurable sets, right. So, these properties should be satisfied for that. Good. So, so far okay. We have actually defined a bunch of things which are actually conceptually fairly simple, okay. Just that the thing is very abstract at this point, right. You probably do not have very concrete examples. I am deliberately keeping it abstract because we can once we develop a proper theory, we can give number of examples and make several special cases, all right. So far logically everything is okay. All right. So, now remember that, see, this phi is in the sigma algebra, right, always, and therefore, omega is also in the sigma algebra, right. So, the whole space is always F measurable, omega is always F measurable. So, omega must have a measure associated with it, because I cannot leave out any F measurable set, correct. So, mu of omega is well defined, correct. So, if mu of omega, so what value can mu of omega possibly take? No, I mean I have not said anything about it, right. So, mu is just so mu maps F measurable sets to 0, infinity, infinity included, correct. So, it could be that this is finite, right. So, this is again something very intuitive, right. If it so happens that your mu assigns only a finite value to the entire space, then it is called a finite measure, okay. And similarly, if this is equal to infinity plus infinity, then mu is called an infinite measure, all right. So, if mu of the entire sample space is plus infinity, then you say the measure is an infinite measure, okay. If it is something finite, you say it is a finite measure, right. And then finally, the case that is of most interest to us is if mu of omega equal to 1, right. It can take any real value, it can be finite or infinite. If it is finite, you say it is a finite measure. A finite measure, in particular if omega is equal to 1, then it is called a probability measure, okay. So, in that sense, a probability measure is a very special case of a measure, right. It is a finite measure, in particular which assigns 1 as the measure to the entire sample space, okay. So, that is really all there is to it, okay. And so, in this sense, probability theory is a special case of this measure theory, okay. So, so this is not a course on measure theory, right, this is a course on probability theory. So, we will not go on and on about generic measure spaces, we will study probability measures in greater detail, okay. So, in particular when mu is a probability measure, when mu of omega is equal to 1, we will no longer call it mu, we will call it p, okay, and we will say omega f p, okay, and we will not call it a measure space, we will call it a probability space, okay. So, because we are studying probability, I want to write it down so that there is no further confusion. So, a probability measure. So, I have already defined what a probability measure is, but I want to do it again, right, just because this is so important. A probability measure, it is denoted by P with 2 lines, okay, standard notation, okay. P on omega f is a function P mapping f measurable sets to, what does it map to? 0 1 now, okay, satisfying is a function that satisfies P of null is equal to 0, P of omega equal to 1, and then if A1 A2 dot 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 are disjoint f measurable sets, then probability of union I equals 1 to infinity A I is equal to sum over I equals 1 through infinity probability of A I. Okay. So, this is just a repeat of what you have seen. So, a probability measure is nothing but a special case of a measure with this additional property. So, the only difference between a measure and a probability measure is that probability has this property, an ordinary measure need not have this property. Its measure can be anything positive, it can be a positive real number or plus infinity. Okay. Okay, so there is one thing I would like to point out again. So, this is an important matter, it could cause confusion. So, this I said, right. So, if you have this union I equals 1 to infinity, or a better notation in my opinion is union I belongs to n A I, right. So, this is the set of all omegas contained in at least one of the A I's, right. So, this union is not defined in terms of some finite union going bigger and bigger or anything like that. However, this summation, right, this is an infinite summation, right. Infinite summation is actually the limit of a finite summation. So, this is like limit n tending to infinity summation I equal to 1 to n probability of A I. Okay. Now, if you write down an infinite summation, the question that comes to your mind is, does it converge, right. I have happily written down this summation, etc. These are infinite summations, right. You have to to make, in order for this to make sense, you have to argue that this is in fact well defined, right. Why is this well defined? Yeah, no, see, when you write a summation like this, the one thing you do not want is, see, you do not mind if it goes off to infinity, then you call this whole summation equal to infinity, right. So, you do not want this summation to be something undefined, right. If you if you write down I equal to 1 to infinity minus 1 power I or something like that, for example, it is something that keeps jumping, right. So, that summation is not defined at all, but such a situation does not arise here. Why not? So each yes. So mu of ai is always non negative. Okay. So if you write down, so if you really interpret this summation is nothing but limit n going to infinity summation I equals 1 through n mu of ai, correct. This is the definition of the infinite sum. So what I am saying is that if you look at that as a sequence in n, call it some x n or something, it is a monotonically increasing, monotonically non decreasing sequence in n. So monotonically non decreasing sequence has to either converge or go off to infinity, which also is in some sense converge, right. What it does not do is oscillate or do any such thing. So if mu i's were not positive, you cannot have this being well defined, right. Similarly for probability measures, okay. Again this is a well defined summation, except what you are constrained here is that after all what is on the left should also be at best 1, right. You cannot, the mapped values can never exceed 1, right. So you have to have a situation where the summation is not only well defined, it has to be at most 1, cannot be bigger than 1, right. Okay, good. And finally omega f p is called a probability space, okay. Okay, so we have come 3 steps, right. So what is a probability space? So you start off with a random experiment and collect all its possible elementary outcomes and make your sample space, and then you collect subsets of the sample space which you think are interesting, which you are interested in assigning probabilities to, all right, and you endo omega with a sigma algebra of subsets of omega, all right. And finally, so then omega f will be a measurable space, then you finally assign probability measures which satisfies these rules, these axioms. So these are called axioms of probability, and these 2 are called axioms of measure, okay. These 3 are axioms of probability, okay. So you end up with a probability measure, right, and this triple omega f p is called a probability space, okay. This is where everything begins with. So this is the beginning of what we are going to build upon. So there is one thing I want to make clear. So this does not tell you, so none of this what we have developed here tells you how to generate these f or how to assign probabilities, right. It does not tell you how to do this, it is up to you, right. But if you were to do it, it just tells you the rules you have to satisfy. Within these rules you can do whatever you want, you can create any f you want satisfying those rules, you can create any p you want satisfying these rules, right. But how you do this, how exactly you do this is up to you, depends on your intention, right, or depends on what you want to model or what you want to capture, right. So it just gives you a framework, it does not give you answers immediately, right. If you supply some numbers to the theory, it will give you some other answers, that is all, okay. So it is your responsibility to create f, create p, etc. Okay. So questions.
Probability, do you assign to elements of sigma or to subsets of?
So as I said, it is a map from f to 0 1, right. So it takes as inputs f measurable sets, right. So in the specific case of a probability, so if you have, so now we are, after all the story we are ready to give a precise definition of what an event is, right. If omega f p, right, if you are looking at a probability space, f measurable sets are called events, that is all there is to it, okay. So you go and put a sigma algebra on omega depending on what is interesting to you, right. Whatever you include in your f is an event, what you do not include in f is not an event, as simple as that, okay. So let me just write that down as well. So, if omega f p is a probability space, so f measurable sets are called events. So, now you have a very precise understanding of what events are. So far we have been giving some wishy washy definition that they are subsets of sample space which are of interest to you, right. Now, this is the correct definition, right. So, in a general measure space, so in the general measurable space you have omega f mu, right, some measure, and the elements of f are called f measurable subsets of omega, and in the specific case of a probability space you do not say f measurable set, you say it is an event, right. Okay. So, there is no difference between f measurable sets and events as far as probability spaces are concerned. Okay. Is that clear to everybody?
Actually, my question is the most elementary element is element in sigma, right?
Sigma, this guy omega.
Yeah, sorry, omega. That is the most elementary thing. If you assign probabilities to that elementary thing, you can always assign probabilities to subsets.
That is not true. So, we assign probabilities to those sets that are in F. F is a sigma algebra on omega, right. You assign probabilities to only those subsets of omega which are in F. So, that F will always contain phi and omega, and it may contain other, it will contain other subsets presumably, but it will not necessarily contain all subsets of omega, right, unless your f itself is 2 power omega. See, f is a collection of sets, it is not a subset of omega, it is a collection of subsets of omega, right. So, unless f itself f is 2 power omega, you will not be assigning probabilities to all subsets of omega, right. What I was saying a little earlier was that when omega is countable, finite or countably infinite, you can actually afford to take f as 2 power omega, and you can assign, it is actually possible to assign probabilities to all subsets of the sample space, right, when omega is countable. But when omega is uncountable, it turns out that if you take f equal to 2 power omega, assigning probabilities consistently to all subsets of something like a real line is not always possible. Okay, this is not something you will understand now. Okay, I will, this is an impossibility theorem, okay, which is a non-trivial theorem. So, if you are working with an uncountable sample space omega, which is like say like real number or 0 1 or something like that, then you have to define a sigma algebra on omega which is smaller than 2 power omega. Okay. So, how you do that is the interesting part. Okay, so that we will get to later. So far any question, any other questions? Yes.
Even for countably infinite sample space, power set will be uncountable.
So that is true. So, if omega is countable, let us say omega is n for example, we know that 2 power omega is 2 power n. So, f will have uncountably many subsets, but that is okay. I am saying if omega itself is uncountable, then it is too big, 2 power omega is even bigger in some sense. So, if omega is 0 1 for example or r, 2 power r is a collection of all subsets of r, right, that is a very huge collection of subsets, and it is too difficult, it is in many cases it is impossible to assign interesting measures on it.
In this case, it is possible to assign probability.
Yes, if omega is countably infinite also you are fine, either omega is finite no problem, omega countably infinite no problem. It does not matter that f has uncountably many subsets, omega if it is uncountable, if the sample space is uncountable you get into trouble. Okay. So, it is you have to be much more careful. So, probability theory is actually very easy when omega is countable. If it is either finite or countably infinite, probability theory is very easy because you can take f as 2 power omega and assign probabilities to all subsets of sample space, which is what you are actually used to, right. But if omega is uncountable you get into trouble. Okay, that is something you may not have studied in elementary courses. Okay. So, I just want to make sure I am done with everything I wanted to say here. yes, we have defined probability space, event is so an F measurable set is called an event. Yeah, so are there any other questions?
Is there any other popular theory other than probability which is based on this structure, measure space?
Well, all of measure theory is, right. So, measure theory is a very important branch of mathematics in itself, and the only thing that is not included is this. Mu of omega can be anything positive or plus infinity.
Special case.
Probability theory is a special case of measure theory, but it is also a very interesting special case. It is a very important special case. But measure theory in its own right is a very important part of mathematics, right. So, even things like length, area, volume, these are all examples of measure. Okay, they just so the concept of a measure generalizes things like length, area, volume, etc. into arbitrary measure spaces, right. I mean satisfying certain properties. Okay, so it's a very important area of mathematics. Is there anything else? Okay, so we will stop the lecture here.